Hello, I'm Alex, and I'm excited to present our work, PlenOctrees for real-time rendering of neural radiance fields. Recently, neural radiance fields, or NeRFs, have gained much popularity in the field. NeRFs were introduced in the ICCV paper last year and made a big impression with these photoreal-looking results in view synthesis. NeRFs have now been used for a variety of related tasks. One of the biggest issues with NeRF is that it is very slow to render. Rendering a single image takes about half a minute, even on a very high-end GPU. This animation is supposed to depict the speed of rendering. This is a problem for practical application and also makes the representation very difficult to visualize. Ultimately, the rendering is so expensive because we need to call the neural network for every sample, and there are hundreds of samples for each pixel, and many pixels in each image. Multiplying these, we get hundreds of millions of network calls to render one image. Of course, evaluating a neural network is already slow. Furthermore, recall that NeRF takes a position as well as a viewing direction as input, so 5 dimensions in total. This would make direct caching difficult. In this work, we seek to tackle this pain point by developing a method to render NeRF in real time. At a high level, our approach is to distill a trained NeRF into a pre-computed octree representation, which we call a PlenOctree. In order to perform this distillation, we first make changes to NeRF to factor out the view dependency. Once constructed, our sparse data structure not only removes the need for network evaluation, but also reduces the number of samples required, cutting down the inner loop of rendering. This allows us to do real-time rendering while keeping image quality high and retaining view-dependent effects. Here's a video of the viewer in operation. As you can see, the rendering is completely interactive. The image quality looks the same as NeRF, and we can capture the view-dependent color. Our real-time viewer also has a variety of features, such as mesh insertion and volume slicing. This viewer can be useful for debugging NeRF projects. Furthermore, I've created a WebGL application to render NeRF in real time in a browser. Feel free to try it out for yourself. Here, I will just show a demo. So I've loaded the mic PlenOctree. Let me now demo some viewer features, like slicing along the axes. Showing the grid for visualizing the octree structure. Shifting the view directions to verify the SH is actually doing something. Or viewing all the cameras used to train this NeRF. I hope that got you excited. So how does this work? Our method has 2 parts, which I will describe in more detail. First, we factor out the view-dependent effects of NeRF using spherical basis functions. Second, we store the NeRF in a data structure which I will call a PlenOctree. Let's dive into the first part. A practical problem for converting the NeRF to an efficient data structure is that NeRF takes the viewing direction as input. While this allows it to model view-dependent effects nicely, the 5-dimensional input space makes it difficult to discretize effectively. Thus, we propose to model view-dependent effects as spherical basis functions which record a color in every direction of the unit sphere. Specifically, we chose to use spherical harmonics, which are a basis for functions defined on the sphere. We propose 2 methods to factor out NeRF's view dependency into spherical functions. For our main experiments, we actually modify the NeRF network to predict coefficients k for each of the spherical harmonics functions. The k encodes the radiance distribution in all directions at the input point. This allows us to model view-dependent color at each point, while getting rid of the view direction input to the nerf. We call the resulting model nerf SH. While we primarily use spherical harmonics in this work, there are also other spherical functions which are popular, including spherical Gaussians and anisotropic spherical Gaussians. Also, we can use learned basis functions such as MLPs mapping directions to colors or spherical textures. The concurrent work FastNerf takes the former approach. Instead of training nerf SH, we can also project a normal nerf directly. While this produces worse results and is slower because we have to sample many directions, it is an effective way for visualizing existing nerfs and is supported in our library. So given a point xyz, we can sample a bunch of random directions on the sphere and evaluate the nerf at this point with all these directions. Then if we also evaluate the SH at these directions, we can use linear least squares to recover the coefficients, even though we didn't train the nerf to output SH coefficients. Either way, we are now ready to construct the PlenOctree from the nerf. A PlenOctree is a voxel-based representation, where each voxel will store these spherical harmonics coefficients, either predicted by the network or fit using the method I just talked about. Of course, this is a sparse voxel representation, so only non-empty voxels are stored. To construct this PlenOctree, we can perform a very simple grid evaluation of the nerf and threshold using the densities. Then we just evaluate and store the SH coefficients, however we got them, as well as the densities in the remaining leaves. This only takes about half a minute to do at resolution 512 cubed. Note that this is only the time needed to render one image with nerf. For the paper, we do perform some very high sample anti-aliasing, which slightly improves the result. With this octree extracted, we render it using simple ray marching. We find the exact ray voxel intersections and render using nerf's volume rendering equation. By varying the parameters of our method, we can trade off speed, space, and quality. Note that our method is more than 3,000 times faster than nerf, and much faster than previous methods for accelerating nerf. We can achieve even faster rendering by varying some parameters and some loss in quality. Now I've described the gist of the method, let's get into a few details. So my immediate issue with such an approach is with cloudy regions. For example, for these scenes where the cameras are all in the upper hemisphere, for the lower hemisphere, the nerf can happily put solid white there instead of empty space. To deal with this issue, we introduce a very simple sparsity loss during nerf training. This loss is the L1 of alphas of randomly sampled points. The loss not only helps to reduce storage size but also with sampling efficiency. This volume rendering model, of course, is fully differentiable. While the quality is fairly good after extraction, we can fine-tune the octree on the training set after conversion to further improve it. This process is considerably faster than nerf optimization. Here's an example of the improvement from this fine-tuning. It's a bit more clear in the boxed region. The PS now improves by 1 to 2 decibels here, and the image is visibly less noisy looking. So one might ask, since this fine-tuning is so effective, could we stop nerf training and convert to PlenOctrees? Indeed, we find that by optimizing the PlenOctree converted the nerf SH checkpoints from earlier training iterations, we are able to reach a similar quality more quickly. We find that it takes 16 hours of nerf training to match the same quality as the PlenOctree model after 3 hours. Note that some nerf training is still necessary, as the PlenOctree structure is not differentiable and has to be constructed from nerf. Here are some more results on the tanks and temples dataset. We have released 2 Python libraries to the public, which you can install with pip. SVOX is the base PlenOctrees implementation with the analytical gradients we use in the paper. NerfVis is quite minimal at the moment, but is intended to be a general nerf visualization system supporting adding meshes and cameras. To wrap up, I just wanted to acknowledge that there are a number of concurrent works. If interested, please do check them out. Finally, our method is not without some limitations. Our main limitation is the file size of the full model, although we are able to compress it significantly without too much quality loss. For large scenes, both model size and rendering speed become issues. We may need more sparsity losses, more efficient GPU voxel volume rendering implementations. It may be good to also look into constructing surface light fields from NERF. We also have issues with bad colors when viewing from a direction not seen during training, more so than the original NERF, because the spherical harmonics have some non-local directional impact. As you can see on the right, these high-degree spherical harmonics are very spiky in different directions. If our views are around the equator, then looking from higher up will result in weird colors. Using SG or other bases may help. Lastly, obviously this representation is also no longer continuous, so you can see voxels if you zoom in. Thanks for listening. Feel free to check out the demo and code.